Okay, welcome to lesson 5.2. In this lesson, we're moving away from reciprocal functions, which have a numerator equal to 1, and we're now going to look at rational functions where the numerator could be any polynomial. So technically, the whole unit is about rational functions, but reciprocals are a special case that we looked at first. Now we're going to look at all of the rest of them. So today's lesson is an investigation. In these investigations, we're always looking at a fraction involving some algebra. So I'm going to call the numerator of the fraction p at x throughout this worksheet and the denominator q at x. And what we're going to be looking at is what happens to horizontal asymptotes for various degrees of the p and of the q. And then we're going to look for some other general rules. We are going to use Desmos to help us figure this out. In our first investigation, we've got 4 different functions we're going to take a look at, and for all of these, the degree of p at x in the numerator is smaller than the degree of q at x in the denominator. So we'll take a look here. In the first one, the degree of p at x, the degree of the numerator is 1. Remember, that's the largest exponent on the x term, and in the denominator, the largest exponent is 2. And then we're going to take a look at, well, what does this graph look like? Where is the horizontal asymptote? So to that, I'm going to flip over to Desmos. And there's our first equation. I'm just adding it to the graph, so I've already typed them in. And when you're investigating these, you do want to kind of zoom in and out and see what's going on here with these graphs. So when I zoom out, I'm pretty confident that I'm seeing what I need to see at my regular zoom. Noticing here that I do cross the x-axis. So this is kind of a weird graph. I just want to draw your attention to that. Is okay. But when I'm looking for a horizontal asymptote, what I'm really looking for is what happens on the very left of the graph and what happens on the very right of the graph. And on the very left-hand side of the graph, what I notice is I am getting closer to a height of 0, and I can drag along here, and I can watch my y values. They're getting closer and closer to 0. And then when I move to the right-hand side of the graph, again, looking at my y values as I drag along the graph, I notice that they're getting closer and closer to 0. So there is a horizontal asymptote at 0. It is okay that I cross the horizontal asymptote near the center of the graph, just not on the edges. So coming back, my horizontal asymptote is at y equals 0. All right, for our second example, hopefully you can read this on your sheet. It's 3x squared over top of x to the power of 5 plus x to the power of 3. So the degree of the top is 2 and the degree of the bottom is 5. Moving over to Desmos, you'll be able to see those numbers a little bit more clearly. There's our second equation there. I'm just going to turn on the color for that graph. And what I see here, again, this looks more like a traditional graph that I'm used to. And again, I'm going to just kind of scroll along as I move to the very edge on the left. I notice that my y values are getting closer and closer to 0. And then doing the same thing on the right, I can see that my y values are getting closer and closer to 0. And again, don't forget to zoom out. Oops. Zoom out and try and make sure that you're seeing all the important bits of this graph, and I think we were from the start. So there again, my horizontal asymptote is equal to 0. Now I haven't set up the next two, so I want you to pause the video at this point, try typing those into Desmos yourself and seeing what those two graphs look like. You want to become familiar with the different shapes of rational graphs. Okay, welcome back from Desmos. Hopefully you found that this guy here has a degree of 2 and the denominator has a degree of 4, that is an exponent 2 and an exponent 4. And then in the bottom one here, we have a degree of 0 on the top, right? There's no x term at all, it's an x to the power of 0. And then in the denominator, a degree of 2. And for both of these graphs, you should have also found that there was a horizontal asymptote at y equals 0. So our summary for this investigation, what was the equation of the horizontal asymptote in each case? It was y equals 0. Taking a look at investigation 2, now we're looking at what happens when the degree of the numerator is equal to the degree of the denominator. So hopefully you find that in each one of these. Here, my first example, the degree of the top is 1, the degree of the bottom is 1, and then they're asking for what is the leading coefficient. So looking at that term that had the highest degree on x, what was the coefficient? It was 2. And then in the denominator, same thing. What was the coefficient? It was 1. And then we're going to go over to Desmos and take a look at, well, what does this look like? Where's the horizontal asymptote? Just getting rid of my last one. Here's the graph we're looking at now. Now, when you start at home on Desmos, this is where what you're looking at. You can see there's a piece of the graph I'm not seeing, so I'm just going to zoom out here. And I'm looking for what values am I getting closer to. As I slide to the left, I'm looking at what's going on with those y values. And I can see like it was started at 2.4 and then it's at 2.3. I'm going to keep sliding here, 2.2, 2.1. I'm getting closer and closer to 2, it looks like. And then I'm going to slide over on the right. And again, sliding along my graph, I'm starting at 1.7, 1.8. I'm getting closer to 1.9 here. So again, I think I'm getting closer to a value of 2 on that graph. So I believe that my horizontal asymptote is at y equals 2. All right, we're going to take a look at the next one. The next one here, the degree of the top is 1, the degree of the bottom is 1, the leading coefficient on top is 8, and the leading coefficient on the bottom is 2. We'll head over to Desmos to take a look at what does this guy look like. There's my graph, and again I can zoom out and I want to take a look at what's going on the left as I slide along. What value am I getting closer to? So I'm starting at 3.8, 3.9, oh 3.94, 3.95. I'm getting closer, it looks like, to 4. So let's check out what's going on the other side of the graph. Again, sliding along, I got 4.08, 4.07, 4.06, 4.05. Oh, I'm getting definitely closer to 4 here as well. So I think that my horizontal asymptote is y equals 4. So this is definitely different than the first investigation. We're going to take a look and see if we can find some patterns. The next one, the degree of the top is 1. The degree of the bottom is 1. The leading coefficient on the top, remember, it's the multiplier in front of the x, so that's a -1. And then on the bottom, the multiplier in front of the x is a 4. When you're heading over to Desmos, we're going to take a look at what this looks like. Oh, I've zoomed way out, so I'm going to just press my home button on Desmos. Takes me back to my center screen, and then again from there I can zoom out a little bit to see what's happening. Again, I want to know what's happening as I slide to the left of the graph. So I can see here I was starting at like a height of -2.8, -2.7, 2.6, 2.61. Okay, and then over here as I slide, I've got negative. Sorry, those ones were -2.6, -2.6. And then here I've got -2.2, -2.3. And I'm just going to keep zooming out because I'm not really confident here. Like I'm somewhere between -2.6 and -2.3. So again, sliding out, -2.5, -2.5. And it's not really getting much smaller there. It's really stuck at -2.53. Let's tell you what's happening over here. -2.45. 4.6, 4.7, and it's kind of stuck there as well. So in between -2.47 and -2.53, I find -2.5. So that's -1/4. And hopefully if I write it as a fraction, you can start to see a connection between those leading coefficients and the horizontal asymptotes. For the last equation, again, I want you to go to Desmos. This is a 3x squared minus 4x on top, and then an x squared on the bottom. So my degrees are 2 on the top and the bottom. The lead coefficient on top is 3, and on the bottom is 1. I want you to go over to Desmos. I'm going to skip this part, but I want you to take a look at what does that graph look like and what is the horizontal asymptote. Okay, welcome back. Hopefully you found that the horizontal asymptote came out as y equals 3. So what we're going to summarize this investigation. Was the horizontal asymptote the same in each case? No, it wasn't. Did I notice a connection between the equation of the horizontal asymptote and the polynomials? Yeah, it looks like to come up with these numbers for the horizontal asymptote, you just take the lead coefficients and divide them. 2 divided by 1 is 2, 8 divided by 2 is 4, -1 divided by 4 is -1/4, and 3 divided by 1 is 3. So I think we just divide the coefficients. Now notice that like when do I know what to do? The first table was all about what happens when p at x, the degree is less. So the bottom degree is bigger, then it's 0 for my asymptote. It's when the degrees are equal to each other. This is when I use this trick of dividing the coefficients. So they've got me to make a guess here. I've got this guy here, the degree on the top is 1, degree on the bottom is 1. So I'm going to use my trick of dividing the asymptotes, or dividing the coefficients to find the asymptote. I think it's -2/5. And then you can check that on Desmos. All right, investigation number 3. Now we're going to take a look at what happens when the degree of the top is bigger than the degree of the bottom. So for this first one here, I've got x squared on top and x plus 6 on bottom, so degree of 2, degree of 1. And then they're asking me to go and actually take a look what happens on the graph as I get really, really big x's or really, really small x's. And that's what we were doing before to find our horizontal asymptotes. So I'm going to switch over to Desmos and take a look at this graph. So here it is here. Again, I don't think I'm really seeing what's going on, so I'm going to zoom way out, and what do you know, there's a whole big section of the graph I was missing. So as my x values get really, really small, so I move to the negative side, the end behavior is getting really, really big. So as I move to the negative side of the graph, I'm getting negative x values, or getting closer to negative infinity, sorry for the y values. And then as I move to my positive side of my graph on the x's, the y values are also getting really, really big. So just moving back to end behavior, right, from our chapter 1. So as x gets really big, y gets really big, and as x gets really small, negative infinity, y got really small. So is there a horizontal asymptote? No, I am not getting closer to a horizontal line. But what's happening, hopefully you can see this on the graph, is I'm getting closer to like a slanted or a diagonal line. These two sections of the graph are lining up in a straight line, and as I zoom out, it almost looks like it forms a straight line there. But it is on a diagonal. So we call that an oblique asymptote. All right, so for our next one here, we've got x to the power of 3 on top. Hopefully you can read those little numbers. And x to the power of 2 on the bottom, so the degree of the top is bigger than the degree of the bottom. We're going to go take a look at what happens with this graph. So I'm going to just go home for a second for my scale. Move over to that equation, and I see this it almost looks like a piece of a cubic graph here, but again, I want to know what's happening on the left side and the right side. So I'm going to zoom way out. Oh, and what do you know, there's another section to this graph, and as I zoom here, again, when I'm sliding to the left side of the graph, I'm getting negative infinity for my y values, and as I slide to the right side, I get positive infinity for my y values. So same as last time. Now, is there a horizontal asymptote? No, there can't be. If I'm going to different infinities on either side of the graph, it's definitely not horizontal. Even if I was going to the same infinities, that would not be horizontal either. So is there an oblique or a slanted? And yeah, you can kind of see it, that as I head to the left or the right, they're kind of lining up into this straight or diagonal line in between them. And so that would be an oblique asymptote. There's like an invisible dotted line between these two sections of the graph here that I'm getting closer and closer to, but I'm never actually going to touch. Just remember, that's the asymptote thing. It's never going to actually touch it. All right, for the next one here, I've got 3 minus 2x plus x squared, so degree of 2, over 1 plus x, degree of 1. We're going to go take a look at that graph. And again, you might start off at home and you would only see this section here, and then you would zoom out until you can see a bit more of the graph. And again, as I move to the left side of the graph, I can see that the y value is getting closer to negative infinity, and as I move to the right side, the y value is getting closer to positive infinity. And then we're going to be looking for a horizontal asymptote. Well, of course, there can't be if I'm heading to infinities on either side. But is there an oblique asymptote? And hopefully you've already kind of spied it. There is there, and as I zoom out, you can kind of see it's almost approaching the straight line. It's not quite, right? It's getting closer and closer to it, but it's never quite getting there. That is an asymptote in between those two. Notice that the question is never what is the oblique asymptote, it's just is there one or not? And that's the only question you're going to be asked in this course, even though you actually already have all the math tools to figure out the equation of that oblique asymptote. I will not ask you to do that in this course. All right, in our last example, we've got an x to the power of 3 on top. So 3x cubed minus 4x over x plus 3, so it's a 1 on the bottom. So a little bit different this time. We're going to take a look at what does this graph look like, and this one's a little bit different. So again, starting at home, I kind of see it almost looks like a cubic again. And then I'm going to scroll out and I'm going to see what's going on. So I was not seeing much, not seeing much. And then all of a sudden there's like this extra little piece here up at the top. And I can keep zooming out here. Now, when I zoom out, it's so skinny. I wish I didn't see all these big X values. So I'm going to go into my scale and I'm going to get rid of all these big X values. I don't want to see them. There we go. And now when I start to zoom out, hopefully we can kind of get a better picture. So I want really big Y values, but not really big X values for this particular graph. It's kind of a weird looking graph. This is unusual. Again, the question here is what's happening as I move to the right side of the graph. And hopefully we can see here as I move to the right, it is getting closer and closer to positive infinity. But the same thing's happening on the left here. So I'm seeing positive infinity on both sides. Again, that means that there cannot be a horizontal line between those. So there is no horizontal asymptote. But what about an oblique? Is there a straight line connecting those two sides, the left and the right side of the graph? And no, there is not. You can see here as I zoom out, it kind of looks like a parabola, and it is. But you don't need to know that right now. All you need to know is there an oblique or a slanted asymptote? So no, there is not. So what do I notice about these rational functions? So when the degree of the top is bigger than the degree of the bottom, what I notice is that there's no horizontal asymptote. Sometimes there's an oblique and sometimes there's not. So let's try and see if we can figure out why is that. And the key is to look at these degrees here. So when I look at the first pair, the second and the third, they all gave me an oblique, but this last guy didn't. So what was different about him? Well, here, the degree of the top was one more, and then all of a sudden the degree of the top was two more. And that's when I did not get a horizontal asymptote, or sorry, an oblique asymptote. So if the degree of P at X is one more than the degree of Q at X, then I get an oblique asymptote. All right, investigation 4. Now we're going to look at what happens when there's repeated factors in the top and the bottom. So to do that, we do need to factor the top and the bottom to take a look at it. So first I've got x squared minus 4. That's a difference of squares. So that's x minus 2 and x plus 2. And then the bottom's already factored. It's just one factor. And what I notice is if I had these two factors on top of x plus 2, I could cancel out the x plus 2. And so my canceled factor would be x plus 2. The x values then that would make that canceled factor equal 0. So what number can I put in for x that makes this whole thing equal 0? That's negative 2, or x equals negative 2. And then I want to look at, well, what happens at those values on the graph? So we're going to head back over to Desmos and type this function in. Oh, we got to go back home here. And this graph, actually, when you zoom out, it looks like a straight line, and it is. But something weird is happening when you get to x equals negative 2. And so you can take your mouse and scroll along until you get to negative 2, but like, it's going to be really hard. Yeah, there, I got it to pop up. And what you notice is you see how here I have a filled in circle, and once I get to negative 2, can you see it there? It pops into an open circle, and that's because I have a hole at negative 2. There's an undefined y value. And it's because if I plug negative 2 into that equation, I'm going to get 0 divided by 0, which is not a defined value for me. So I get a hole at x equals negative 2. So let's take a look at the next example. We've got x plus 1 as the factor on top, and on the bottom I've got the factors x plus 1 and x minus 3, right? What multiplies to negative 3 and adds to negative 2? Positive 1 and negative 3. So the factor that would cancel there is x plus 1, and the x value that would make this thing equal 0 is x equals negative 1. So I'm going to go look at negative 1 on the graph of this guy. All right, so here's my graph. I'm going to just go back to home so it's zoomed in a bit. I'm interested in x equals -1. So I'm going to grab my cursor and just slide it along the graph until I get close to x equals -1. I'm going to try and stop right at -1. And there it is. It turns into a hole. The point is undefined only at -1. So once I pass by -1, it is continuous again. And again, that's because if you were to plug -1 into the numerator, you would get 0, and into the denominator, you get 0 times -4. Well, that's just 0. So 0 divided by 0, that again is undefined. All right, our next one, we're going to factor the numerator, what multiplies to 6 and adds to -5. So we get x minus 2 and x minus 3. And then on the denominator, what multiplies to -2 and adds to -1. So we get x minus 2 and x plus 1. And then the factor that's going to cancel here, the repeated factor, is x minus 2. And the value that would make that thing equal to 0 would be x is positive 2. So again, we'll go and take a look at the graph. I think no surprises here. I'll get rid of the last one. Again, we're going to be taking a look at what happens at x equals 2. So I'm going to grab my cursor, slide along until I get to 2, and there it is. It's undefined. There's a little hole. And when I get it exactly, there it goes. The cursor actually changes to an open circle, which is how I'll draw it on a graph. All right, so we're going to summarize. What did we figure out today? Okay, if I'm given a function that looks like this, p at x on top of q at x, then first thing I'm going to check for is what kind of situation do I have with the degrees. If the degree on the top is smaller than the degree on the bottom, then the horizontal asymptote is y equals 0. If the degrees are equal to each other, then I have to take a look at the leading coefficient of the top is a, the leading coefficient of the bottom is b, then the horizontal asymptote is going to be a divided by b. If the degree of the top is bigger than the degree of the bottom, then there's no horizontal asymptote. Now, if the degree of p at x, so I'm still kind of, these guys are connected. If the degree of p at x is 1 more than the degree of q at x, then I have an oblique asymptote. You guys do know how to find the equation of the oblique asymptote. It involves long division, but we are going to skip that. So you just have to tell me yes, it exists, or no, it does not exist. All right, and then the last one, if p at x and q at x have a common factor of x minus a, right? So that means I can rewrite them with, each of them would have a bracket or a factor of x minus a. That means I could cancel those out, and I would get a hole at x equals a. So it's minus a in the bracket, then the hole is at x equals positive a. All right, have fun with your homework.